Hello everybody, my name is Barisha and we are talking about Vera Rubin architectures. Vera is a CPU and Rubin is a GPU. Unlike the GPU, Rubin, for which, let's say, wider documentation for the explanation of the internal architecture is still unavailable. Just some glimpse of the explanation of the architecture for the Rubin GPU is available on the blog, NVIDIA blog. Vera CPU is actually now with documentation, which can be seen here. It have 45 pages, and NVIDIA Vera CPU architecture, max single thread CPU at scale for agents. So this is mostly for the agents or efficient agents. Okay. We see the chip. This is Vera CPU, and it have 88 Olympus cores, and they are double threaded. And we mentioned that characteristics in previous videos. But let's now go further. Maybe there will be some repetition, but it doesn't matter. We will meet new stuff of the architecture and make documentation introduction from the documentation of the architecture elements. So first thing first, this is NVIDIA Vera CPU, and let's see the communication. One of the communication links is given here and shown here, which is NVLink chip-to-chip communication, and in standard standard explanation, NVLink chip-to-chip, it's like in a GPU. Rubin GPU, the bandwidth is 1,800 gigabytes per second. Coherent CPU to GPU interface. So this is a CPU to GPU interface. And in configuration, in a super chip where there is one Vera CPU and two Rubin GPUs, half of the links is going to the one GPU and half of the links is going to another Rubin GPU. And that super chip configuration with one CPU and two GPUs, it's all NVIDIA chips. So that's the standard configuration for these NVL structures. And we will make one short where we explain possible ways to make interconnections between chips of the different manufacturers, but in this case this is the same manufacturer for the CPU and for the GPU. Also, it says monolithic compute die. In previous case we talk about Rubin GPU, which is actually dual die, let's say composite. Also 88 NVIDIA custom Olympus cores with 176 threads. We explained that in previous videos. This is the amount of L3 cache, 164 megabytes. And it says here second generation NVIDIA scalable coherency fabric. Okay, we will see in documentation what does it means. And we have also here confidential computing, TEE input output capable. So we mentioned that also with the Rubin GPU architecture. And times 16 PCI generation 6 or CXL for the communication with other devices. In previous videos we explained this link because there is explanation that it's same with the Rubin GPU. Also, we said that speed rate or bandwidth for the PCI Gen 6. Also in the in documentation it says generation 6.4. Okay. We mentioned that speed is 156 gigabytes per second, I think. And what we can see also in the architecture, there is a lot of, not a lot of, but exactly 8 these LPDDR controllers, which are managing the data flow between DRAM memory or outside memory, which memory? LPDDR5X memory, or exactly this one. And there is 1, 2, 3, 4, 5, 6, 7, 8 of these controllers, which are controlling data flow and the rate of the data transfer from the DRAM towards the CPU. The rate of total amount or total memory bandwidth is 1.2 terabytes per second, which is I think pretty much for the CPU and this kind of memory. And total amount of memory which can be attached or joined to this CPU unit is 1.5 terabytes. A type of the memory is SOCAMM, and it's low power DDR5X memory. So we make short introduction. We see the communication links and control with the control of the external DRAM given here, and 88 Olympus cores, which are not single threaded but double thread. So we have 176 threads. So let's go further. What did we said? Branch prediction. Yeah, we didn't mention that, but of course, branch prediction is main topic on the CPUs, and it says that neural special purpose predictors, this is the type, so neural special purpose predictors, 2 taken branches per cycle. So okay, we will see. This is just to mention stuff. Introduction decode, 10 wide, prefetcher, novel graph, and advanced prefetchers. L1 cache, so data cache, it's 96 kilobytes, and instruction cache, L1 instruction cache is 64 kilobytes. L2 cache is 2 megabytes, and L3 cache, like we mentioned before, so it's wider and probably for all cores can reach it. It's 164 megabytes. Also, we mentioned that, no, we didn't mention, but memory bandwidth per core is 14 gigabytes per second. So NVIDIA Vera CPU integrates 8 LPDDR5X memory controllers, like we mentioned and so before, and so on that picture. Total memory bandwidth for NVIDIA Vera CPU for all 88 Olympus cores with 14 gigabytes per second is 1.2 terabytes per second, and the memory capacity is up to 1.5 terabytes LPDDR5X for this type of CPU and for this architecture. Also, power efficient LPDDR5X memory. This is for the data center class. This is a data center class memory with the ECC error correcting class. Also, power consumption for this type of CPU is from about 250 watts up to 450 watts, which is big, but in comparison with the, let's say, GPU, I think it's pretty much lower. Also, ARM architecture is 9.2, ISA support, and Olympus was designed to accelerate the irregular branch heavy and latency sensitive software paths that increasingly shape end-to-end AI factory performance. So this is for what and how they designed for these tasks. So irregular, branch heavy, and latency sensitive software paths that increasingly shape end-to-end AI factory performance. So in further, when we go and walk through the documentation, we will explain much more in capacity we can this stuff. But yeah, maybe it's time to speak about these predictions. They are branch predictions. They are regular stuff, and usually we have, let's say, fetch, decode, and execute. So we need to explain this stuff a little bit wider and deeper, and with more sense and understanding. So, and up till then, I think we said enough for this video, so we can stop here. Until next video, bye bye.